So look at the next paper, Mind Minds, Galamsey in Ghana, a test of the Lucifer effects by Tego'S.
Yes, sir. Good afternoon, ladies and gentlemen. My name is Maxwell Kofi Tego. I'm a researcher with Spear Institute with a background in materials engineering and advanced concrete technology. Just as a major correction, I'll be presenting on trash transformed. It is a study, an engineering study to attempt to solve some of the sustainability problems and issues we have even in our society, even in our environment. And we see it fit as engineers in the construction sector to bring about sustainable measures even in our practice of engineering. Okay, whilst my slides are being prepared, I would want to quickly move on because of time. So, the study has to do with producing concrete, which is the first most used man-made material on earth. Concrete. And everyone has seen concrete before. I presume so. If you haven't, please, you can just look at your left or right. You would see some walls and then construction has to do with concrete. Concrete is the second most used aside water. So our study had to do with 100% replacement of natural aggregates, that is the sand and the gravels, with waste materials. And the waste materials were glass and plastic. So this is what the study is all about. And I would want to share some key findings with us, and then we'll see some of the interventions we can outline to promote sustainability even in the field of construction. Please, can we go to the next slide? Can we skip the presentation outline to the background? Oh, okay. Okay, thank you. So the background focused more on the problem at hand, which I know from the discourses we've had so far, even from yesterday to now, we've seen a lot of disadvantages that had to do with our unpreparedness to embrace sustainable measures in our respective spheres. And this particular slide captures a lot, but I would want to highlight just two or three of them because of time. The first point says that the construction industry causes 8% of global CO2 emissions. This number is very staggering. You would see it as a very small number, but I tell you, it is not as infinitesimal as it looks. The 8% is of weight. Because we have students here, I would want to slightly talk about the carbon emissions. When we talk about carbon emissions and our need to prevent them, CO2 has an advantage for animals. It is good for plants, even for humans. But in excess, we don't want it in our environment. We don't, because CO2 is a greenhouse gas and it prevents infrared radiations from going out of space from the earth. And this is what leads to the increase in temperatures and the climate changes we are experiencing across the globe. So we are doing our very best to solve this particular issue. The construction industry also consumes 25 to 30 billion tons of natural aggregates annually. This is just per year. We are consuming 25 to 30 billion tons of natural aggregates. The natural aggregates there refers to our river sand and our gravels, our stones that we use in concrete production. The third point you see there highlights the fact that approximately 400 million tons of plastic waste and 100 million tons of glass waste are generated annually. And out of this staggering number, we have 10% being recycled. So the question now is, where are the 90%? We find most of them in landfills. We find most of them in drainage. We find most of them unaccounted for. So there's a need for us to take action in that wise. Now, moving on. Why did we intend on choosing waste glass and plastic? From my just mentioned point, 100 million tons of glass waste is generated annually. And only 10% of it have sustainable accounts, that is recycled. But the 90%, statistically, we don't know where we can find them. Aside this social truth, there's an engineering aspect to we selecting waste plastics or waste glass. Waste glass has a component called silica, and this silica gives the glass a pozzolanic effect or a pozzolanic nature, which also contributes to the compressive strength of the concrete composite matrix that is formed. And also the LDPEs, the low density polyethylenes, that is the polyethylene bags that we see often. It has a density of 0.91 to 0.94 grams per centimeter cube, which would make the concrete lighter. We are into spearheading sustainability in construction and also innovation. 2 years ago, I visited a town in India called Nashik, and I was sent to an AAC plant, an aerated autoclave concrete plant. And I was handed a very big sample of concrete. I was told it was concrete. I didn't believe it. It was as light as paper, and I'm not exaggerating. It was very, very light, low density. And this concrete you are seeing has an MPa of 50 MPa. We have 60 big, high compressive numbers. And it is as light as paper. So this is where engineering is getting to us. This is where construction is getting to us. We are thinking about sustainable ways and more innovative ways to ensure that construction becomes a more safe place for we engineers and also the general public at large. So what was our aim? Our aim, one, I'll read it as soon as we have 4 minutes. Okay. To investigate the compressive strength and performance of concrete made with 100% aggregate replacement using waste glass and plastic. Our methodology, how did we go about it? Of course, we got our raw materials from the landfill. We washed them thoroughly. Let me quickly go through. We washed them. You could see the transition, the pictures on your screens. So we gathered the waste materials. We washed them. The hands you see there are my hands. Oh, okay. Let me go to the back. Yes. So the second picture, the hands you see there are these hands. So we washed them manually. We used the mortar and pestle. We crushed them, and then we sieved to get the 0 to 4 millimeter diameter waste glass, and also the coarse for the coarse aggregate. We also had our plastic waste. We cut them into a reasonable diameter between 4 mm to 8 mm, and we mixed them with the water and also a dosage 0.8% cement weight of super plasticizer. And then we had our concrete composite material there. We cured it for a period of 7 and 28 days. So these are the results. Now, it will surprise you to know that even as literature had already given us an insight with what we should expect concerning our testing and our findings from our waste glass composite material, it was a bit shocking to find out that one of our samples with 78% glass and 22% plastic almost rubbed neck and shoulder with our control mix after 7 days. The mix design used was 1.53. The control mix you see is the last on the table, and it had 17.2 MPa. But when you glance to the top, sample 3, you could see that it had 13.07. These results brought promising hope for us. We were very excited with what we were doing, so we had to go for the 28 days. And then we had a reduction, the same sample 3. We had a reduction. Now, the explanation for this reduction has to do with the ITZ. In concrete technology, there's a phrase called the interfacial transition zone. It is like the canvas for an artist. It is where all the drama in concrete happens. The concrete matrix you see, it goes beyond the aesthetic looks. There are intrinsic properties that determines the performance of concrete, and it all happens at the ITZ. When the ITZ, what happens at the ITZ controls the property of the concrete. But for the sake of our study, we didn't go into details. We didn't go into the SEMs. We just had to estimate the compressive strength of the composite material. Yeah. So the practical implications, I'll just outline some of the practical implications. What does this research or this study tell us? What can we gain from it? We've combined waste, glass, and plastic. So now what is our next step? What does it imply on the construction space and even we sustainable agents at large? In the field of construction, it can be used for, of course, not non-structural members. As per Ghana's Building Code 2018, it has been given that the compressive strength for structural purposes should be 25 MPa, but we weren't able to achieve 25 MPa. But it could be used for non-structural members like pavements and other low compressive strength required members. Environmentally, we are reducing carbon emissions, of course. Economically, it lowers raw material costs by 25 to 30%. Socially, we are encouraging local recycling, industries, and green job creation. Future research should focus on one I mentioned, the SEMs, to just find a very good report on the ITZ, because there's a lot that can come out from the mixing of waste, glass, and plastic. There's this term I'm trying to bring to remembrance. The ASR, the alkali silicate reactions. There are a lot of reactions that chemically would have to go into to be able to dissect the happenings in the concrete matrix. Also would want to focus on exploring the microstructural properties, as I said, optimize glass to plastic ratio using design of experiments, AI modeling, and also we have to investigate the scalability for large-scale applications and regional material variability. Ladies and gentlemen, this is a study from Spear Institute. Thank you so much. Have a nice day.